welcome to another video. In today's video, we will be wrapping up chapter 6, Electrolysis. Today we're going to discuss electroplating, refining of copper as the remaining applications on electrolysis, and then we will take a look at the hydrogen-oxygen fuel cell, and with that this chapter will be done. So for the first part, we have electroplating. What is electroplating? It's basically when you want to cover one metal or an object with a different metal. Say, for example, you have a spoon. This spoon is made of stainless steel, for example, and you just don't like how it looks. And of course you can't afford to go and buy a spoon made of silver because it's really expensive. So what we can do is go ahead and cover this spoon with another metal, a more beautiful, a shiny metal, something like silver, for example, or copper, or gold, sometimes chromium as well. These are the metals that are used commonly to cover other metals, or in electroplating. Nickel as well is used in this process. So you have silver, copper, gold, chromium, because it protects the metal from rust or oxidation, and nickel as well because it also protects from rust and has a shiny look. So how we can do this process? We need to prepare an electrolysis cell. In order to do that, we need to bring our object that we are trying to electroplate here. Let's say it's going to be a spoon or a vase or whatever it's going to be. Let's presume that this is a vase. It's not the most beautiful vase, but let's just presume that this is what we're trying to electroplate here. And we are gonna electroplate it with silver, for example. So we're gonna need a source for silver. The source for silver would be basically a bar of silver. We'll just say that this is our bar of silver. And we're gonna have to connect these two to a battery to make sure that there is a flow of electrons, obviously. Now the question is, who do we connect to the positive pole and who do we connect to the negative pole? Well, in order to answer this question, we need to understand what's happening in this cell. So at the anode, which as we know is the positive pole, or more like connected to the positive end of the battery, we're gonna have silver. And this silver, give me 1 second while alright, this silver is gonna be turning into silver ions. Why it's turning into silver ions? Because we're passing an electric current into it, and at the same time we have a solution which is the electrolyte, which we will get to in a second. So this solid silver is going to be turning into silver ions, aqueous. And how it's gonna do that? It's gonna lose electrons. And we've agreed that at the anode, oxidation happens, and oxidation is loss of electrons. If you recall from the previous videos, silver has only one electron at its outer shell, so it can only participate or lose only one electron. We can call this process oxidation, or we can give it another name. As you can see here, this solid silver turned into an ion, so we can call this ionization because we formed an ion. Okay, So this is what's happening at the anode. Now at the cathode, which we agreed is connected to the negative pole of the battery, what happens is the silver ions. Now, if you're wondering where the silver ions came from, you might be thinking, okay, they came from this silver. Well, you would be partially right. However, to be more accurate, the silver ions actually came from the electrolyte. As we've agreed, we cannot have electrolysis without having an electrolyte, which is a solution in which we are dipping these two guys here. And that solution has to contain ions of the metal that we are trying to electroplate. So for example, here we are trying to electroplate this vase with silver, which means that our electrolyte needs to have some Ag plus ions. Okay, so what is the best option for us to have some Ag plus ions? That would be silver nitrate, so AgNO3. So we're gonna have NO3 negative and Ag positive in the solution here. All right, so we have some of those, and of course we have a lot more than that in here, but just for demonstration, our electrolyte would be silver nitrate. And of course, as we've agreed in the previous videos as well, nitrate and sulfate, they never ever discharge. All right, so what we have discharging here would only be the silver ions. So get back to our equation, or what's happening at the cathode is that this silver ion is going to be gaining one electron, which is this electron right here. Here we go. And it's going to be forming solid silver. This solid silver is going to go ahead and precipitate all over our vase, hence covering the vase with silver, or the spoon, or whatever it is that we are covering. Now, in order for us to make sure that our vase, spoon, or whatever it is that we are electroplating is getting covered well, we need to make sure of a few things. First off, we need to make sure that we clean our vase or our spoon with cotton wool and sandpaper before we start electroplating. Why? Because we need to be sure that the copper or the silver or whatever it is that we are electroplating with would stick to the surface of the vase or whatever it is that we are electroplating. Any impurities, any sand or anything stuck on the vase could prevent silver or copper or nickel or whatever from sticking to the surface of the vase that we have. That's for one thing. Another thing that we need to make sure of is that we are rotating the vase, or we are rotating the spoon. Why? To be sure that it gets covered with silver from all directions. So these are the two things that we need to make sure of. Now, getting back to our equations here, so at the anode, we agreed that the silver is going to be getting ionized. At the cathode, the silver ions are going to be turning into solid silver. Now, if you notice that the silver ions had a positive charge, however, the solid silver has zero charge, it doesn't have any charge. So what happened in this case is called discharge. Why? Because we lost the charge. So this means removal, basically. So what we did is that we removed the charge from the ions. So at the anode, ionization happens. At the cathode, discharge happens. All right? Now, we agreed that we're going to be connecting the silver bar to the anode, just to be sure that it's the one that's getting ionized. So let's make sure that this is our positive pole, like that. and we agreed that we're going to be connecting our vase or whatever it is that we are electroplating to the negative pole. So let's just make sure that this is our negative pole right here. Okay, now just as a reminder, this is a bar of silver and this is our vase. This would be our electrolyte, which is silver nitrate, AgNO3. Okay, so again, what is the point of electroplating? You know, getting shiny, beautiful appearance for objects and protecting from corrosion. What do we observe while doing this experiment? First off, we notice that our anode, which is this bar of silver, it starts getting smaller. Why? Because the silver, the solid silver, keeps on jumping into the solution and turning into ions. So it starts corroding or it starts getting smaller. All right, that's for one thing. For another, if we have, let's presume that this means it's getting smaller, right? If we have a bulb right here, for example, let's say that this is a bulb, do you expect this bulb to illuminate or give out light or not? Well, we agreed that there is a flow of electrons coming from here, going here, passing through the anode, and then ionization happens, discharge happens, electrons go here and move back into the bulb, so it would start giving out light. All right, so just make sure if when you're reading the question to see if there is a bulb in the question or not, because if there is no bulb in the question, then we're not expecting any illumination to happen. The third observation that we have is that our vase, spoon, whatever it is that we are electroplating is gonna start like getting covered or coated with silver or gold or whatever it is. All right. Now, the last thing we want to talk about in electroplating would be the role of the electrolyte. Like, what's the point of the electrolyte? The electrolyte is doing mainly two things. The first thing, it's allowing the flow of electricity. And the second thing, it is keeping the concentration of silver ions constant. Now, why is it keeping the concentration constant? Because the rate at which silver, let me just add some color here, orange, so not orange, there we go. The rate at which silver is turning into silver ions has to be equivalent to the rate silver turns into oh, actually I missed the plus here, I'm sorry. Yeah, there we go. The rate at which silver, solid silver, turns into silver ions has to be equivalent to the rate at which silver ions turn into silver. Okay, so the rate of ionization basically has to equal the rate of discharge. Okay, so let's just go ahead and add the plus to indicate that this is an ion. Don't ever forget this plus, because otherwise you're not going to get your grade, because you need to be sure that you know that this is an ion, and because it's an ion it has a charge. So again, the role of the electrolyte is allowing the flow of electricity or conducting electricity and keeping the concentration of silver ions constant during the electrolysis process. Why? Because the rate of ionization of silver to silver ions has, at the anode obviously has to be equal to the discharge rate of silver ions to silver at the cathode. So those are the main points that you need to know about electroplating. Just make sure in the question you know or you pay attention whether it's asking you to electroplate using um, silver, for example, or using copper, or using gold, chromium, nickel. Just pay attention to the number of electrons coming out. Because, for example, in the case of copper, it would be losing 2 electrons. Silver and gold, it would be losing a single electron, so on and so forth. So that's it for electroplating, and let's move on to the refining of copper. Alright, everyone, so now let's get into refining of copper. First, let me tell you a quick story about where copper comes from. So, copper comes from an ore called malachite, which is this green rock that you see here. And of course, as an ore, it does have some impurities stuck in it. So what we do is that we get malachite, which, by the way, is it's just copper carbonate, CuCO3. And by thermal decomposition, which means that we need heat on this arrow, it decomposes when you expose it to heat, and it turns into copper oxide and carbon dioxide. Right now we have copper oxide. We still don't really have copper. So what we do is that we just need to get rid of this oxygen atom. So how do we get rid of oxygen? By adding an element or a compound that's hungry for oxygen. And that's going to be a reducing agent. And one of the most common reducing agents that we have is carbon monoxide. Carbon monoxide takes this oxygen atom and forms carbon dioxide right here, leaving this copper by itself. Now, if we want to talk about this reaction here from a redox perspective, we're going to discuss it as follows. So, carbon oxide is going to be our reducing agent, while copper oxide is going to be our oxidizing agent. As we've agreed in the previous videos, the process that happens to reducing agents is oxidation. So the process here is oxidation, while the process that happens to oxidizing agents is reduction, because when you think about it, copper oxide lost an oxygen atom, so it technically got reduced. So the process here is reduction. Alright? If you want to think about it from the concept of gaining and losing electrons, by all means. If we look here, the oxygen has a valency of -2, copper has a valency of +2, because this is a compound. Now for copper, it turned into solid copper, which has no charge basically, so there's a zero here. So what happened is that copper gained 2 electrons, and as we agreed, gaining of electrons is reduction, while losing electrons is oxidation. So the process that happened for copper oxide here is reduction, as we agreed. And you can think about the exact same process for carbon monoxide as well, and you will find that it turned into CO2, so the valency for carbon changed actually. I don't want to dive deep into carbon monoxide because carbon has so many valencies. It can be 2, it can be 4, and we're going to discuss that in organic chemistry later on. So I just don't want to confuse you with carbon monoxide for now. However, all you need to know is that carbon monoxide is it's drawn like this, C double bond O. Alright, while carbon dioxide is written like this, C double bond O, double bond O. So technically here carbon is forming 4 bonds. Here carbon is only forming 2 bonds. Can carbon do that? Yes, it absolutely can do that by all means. However, when it comes to stability, of course, carbon dioxide is more stable than carbon monoxide. Again, we're going to be discussing all of that in organic chemistry. However, the valency for carbon did actually change from 2 to 4, which means that it did lose electrons, which is oxidation basically. So let me just remove that because I don't want to confuse you. What is going on? Low. I'm trying to erase it. Yeah. Oh, okay. Now that was the story of malachite, the green rock or the green ore from which we get copper. However, keep in consideration that the copper that we get from this process is still impure copper, and this is where electrolysis plays a role. We use electrolysis or electrochemistry to refine this copper to make sure that we have a more pure form of copper. So if we imagine that we have this here as impure copper, and we put it in a tank with a bar of pure copper. And right, this is pure copper, and one end is going to be connected to the positive of the battery, the other end is going to be connected to the negative, but I'm not going to tell you which is which now until we talk about the reactions happening at both the cathode and the anode. Let's say that we connect the battery and wait, is anything gonna happen? No, nothing's gonna happen. This is just like you holding the impure copper in one hand and the pure copper in the other hand, connecting them to a wire. Nothing is gonna happen at all. Why? Because we don't have an electrolyte. So we need an electrolyte in order to allow the movement of ions and electrons, conduct electricity, and allow the process to go through. The electrolyte that we're using in this case is gonna be copper sulfate. So we have Cu2 plus SO4 2 minus. We have a lot of these ions in here, and now our cell is ready, and actually something is going to happen when we connect the battery. Now what's gonna happen is as follows. Let me just pick another color. Alright, so add the anode. We agreed that at the anode we have oxidation. Oxidation is the process of losing electrons. So what do we have here that can actually lose electrons? Well, impure copper or copper ions can lose electrons. Copper itself can lose electrons, not copper ions. Copper can lose electrons and turn into copper ions, and that's exactly what's gonna happen. So let me just get back here. Copper is going to lose how many electrons? It's going to lose 2 electrons. Why? Because as we agreed, copper has 2 electrons in its outer shell, can participate with 2 electrons in chemical reactions. 2 plus, and we have 2 electrons right here. Well, this is obviously solid copper. This is an ion, so it's an AQ, and this is just an electron, right? So this is what's happening at the anode. Now, what's happening at the cathode? Let's just get another color. At the cathode, we have reduction. So what happens is that the copper ions coming from the solution here, or from the electrolyte, to be more accurate, will be gaining the 2 electrons that were lost there, and we're gonna have solid copper again. The solid copper is gonna be precipitating at the cathode, so this is solid copper. Alright, so what's happening is this is gonna be our anode, so this is gonna be connected to our positive pole for the battery. This is gonna be our cathode. Why? Because this is the one that has the original solid copper that is gonna be losing electrons and jumping into the solution here to join the other copper ions in here. And then we have some of the copper ions which are going to be precipitating right here in the form of solid copper. So we're going to notice that the volume or the size of the cathode is going to be increasing as more copper is getting precipitated on it. All right. So let's get back to our notes real quick. All right. So these are the cells here. So we have an anode, which is impure copper. There we go. We have a cathode, which is pure copper. And this is a sludge containing precious metals, which is other, or basically the impurities that we had mixed up with our copper. This is going to start losing weight as the copper keeps on moving from the anode to the cathode, and you will see that it keeps that the copper keeps building up at the cathode, as you can see here. While when the anode is almost gone, the anode and the cathode are basically the anode and the cathode are basically replaced, because we need the process to keep on going, so we need to refine more and more copper, so on and so forth. All right. Now there's something that I want you to notice. In here, we perform this process using active electrodes. Active electrodes. Because we basically used copper in this process. We can perform the exact same process using inert electrodes. Now, how we can do that? Let me show you. So, as we agreed before, inert electrodes are either carbon or platinum. Those are the inert electrodes that we have. How we're gonna build our cell is gonna be as follows. So, this is the tank. This is the first electrode made of carbon or platinum, whichever you prefer, connected to one end of the battery. And then we have the other part, which is the other electrode. It has something different. It's also made of platinum or carbon, but it has a layer of copper on it. Okay. Second. So let's presume that this yellow part is the layer of copper put on the other electrode. Of course, it's going to be connected to the other end of the battery, right here. Okay. Now this is done in a slightly different manner. So for inert electrodes, at the cathode, which is the negative pole, which is the coating of copper on platinum or carbon, copper ions are going to be gaining electrons, forming copper, same as the previous process. Now, what happens at the anode? Um, we don't have copper to lose electrons. So who's gonna be donating electrons in this case? Also, who's gonna be our electrolyte? All right, let me answer all of these questions for you. First off, who's gonna be our electrolyte? Again, it's gonna be copper sulfate. However, take in consideration something very important, that this is called copper sulfate solution, which means that it's not only copper sulfate, but it's also water. So here we have Cu2+, we have SO4 2 minus, we have H plus, and we have OH negative, which is water, as we agreed. Water is H2O, which is basically OH negative and H positive, basically. All right, now let's look at those ions in here. By logic, which one has more electrons that it can donate? Well, on the first sight, you might say, all right, sulfate. The sulfate ion has 2 electrons at its outer shell. It can go ahead and donate them. Is that correct? No. Why? Because we agreed from a few moments ago and in the previous videos that sulfate and nitrate, those never discharge, right? So those two, no way, they're not going to be losing any electrons, they're just going to be staying in the solution. Copper 2 plus, well, it already lost electrons, it doesn't even have any electrons. H plus, same story. So the only ion that we have here that can actually lose electrons is the hydroxide ion, the OH negative. If you go back to the previous videos where we talked about where we talked about electrolysis of water, you will remember the very famous equation that we had for water electrolysis, which is basically that 4 hydroxide ions lose 4 electrons, forming 2 molecules of water and 1 molecule of oxygen. All right? It's easier to just memorize the equation rather than have to deduce it from the beginning every time, just for the sake of your time during the test. And the more you write it down, the more you get used to it. So let's get back here and okay. I just want to do something real quick. Give me a second. Yep, there we go. So I just care about colors, sorry. At the cathode, and up here we have at the anode. Okay, so at the anode, we agreed that who's gonna be losing the electrons this time? It's gonna be 4OH negative, AQ of course. We agree that it's gonna lose 4 electrons, forming 1 molecule of oxygen and 2 molecules of water. Now this is a liquid, this is a gas, this is just an electron. The cathode, it's the exact same equation, that's why I wanted to write it down in the same color. So Cu2+, which is copper ion, just add the AQ here, right? We'll be gaining 2 electrons. Oh, actually, there's something that we need to notice. Well, in this case here, we have 4 electrons, right? So these 4 electrons are going to be participating in the reaction here. So we have 4 electrons, and let's see how much copper it's going to form. Well, when you think about it, 1 copper reacts with 2 electrons. So how much or how many copper ions do we need to react with? 4. We need 2, basically. And how much copper is that going to give us? It's going to give us 2 Cu solid. Okay? Now, can we just divide this equation by 2? Absolutely. However, in this context, you need to show that you understand that hydroxide lost 4 electrons. So those 4 electrons have to participate in this reaction. So that's why we need to mention that we have 2 copper ions reacting with 4 electrons, forming 2 solid copper molecules, right? Now, what do we notice in this reaction? A couple of things. Well, first off, copper sulfate is a blue solution, and as this reaction goes on, the amount of water increases, which leads to diluting that solution, which means that the color of copper sulfate is going to be fading. That's the first thing. The next thing is that at the anode, there are going to be bubbles because we have oxygen gas forming in here. So we have bubbles of oxygen, and we have the blue color fading due to the formation of water, which is basically diluting the solution. Now, copper and oxygen produced, this fits the rule on page 105. If you're wondering what's on page 105, this is page 105 in this in the student's book, where I got the text and the equations from. I understand this might be an older textbook, but it's the exact same material and everything. But this is basically page 105. It's just telling you what gas would be forming at the anode, what compound would be forming at the cathode, so on and so forth. And in case of different electrolytes, what you get as well. Feel free to pause and read it. It's not anything that we didn't talk about before. It's also mentioning the increasing reactivity of the different elements like potassium, sodium, calcium, so on and so forth. As you can see, hydrogen is more reactive than copper and silver. So that's basically it for refining of copper. Just make sure that we didn't miss anything. One important question. Why do we have to refine copper? Well, basically because impurities reduce electrical conductivity, because as we discussed, impurities are just other compounds or other materials that could be like poor conductors to electricity, so they will be impairing the electrical conductivity of copper. So in order to improve electrical conductivity and reduce electrical resistance, we refine copper. And of course, if copper is rusty or it's impure, that increases electrical resistance, leading to overheating of circuits, electrical circuits, which leads to damaging them. All right. So refining of copper is done, and we agreed that it can be done in 2 ways, using active and inert electrodes. The last thing that we want to talk about would be second, the hydrogen oxygen fuel cell. Well, in electrochemical cells and batteries, we transform chemical energy into electric energy. Previously, what we were doing is that we were transforming electrical energy, and that's why we had a battery, into chemical energy, or performing a chemical reaction using electricity. That's basically what we were doing. However, in hydrogen oxygen cells or in electrochemical cells, we are transforming chemical energy into electrical energy. And that's why this is a fuel cell, because it's giving electricity. This fuel cell, by the way, is used in cars. However, it has some drawbacks that we're going to talk about in a minute, that make it not that common. We don't really see it that much for a few reasons that we will be discussing soon. Now, um, the fuel cell is an electrochemical cell which is supplied continuously with oxygen and hydrogen gases. Just in case you would be wondering where the hydrogen and oxygen are coming from, we are continuously providing the cell with hydrogen and oxygen. Just to give you a bigger picture, this is basically what it looks like, the hydrogen oxygen fuel cell. So here we have a hydrogen tank. At the negative pole, we're no longer calling them anodes and cathodes in the hydrogen oxygen cell. This is the only place where we're not calling it an anode and a cathode, because it's gonna confuse you, and it's actually like reversed, because this is like it's the opposite of the previous cells that we were talking about, because in here you're using chemical energy to chemical reactions to produce energy, while previously it was the other way around. So here it's just going to be enough for us to mention that we have a negative pole and we have a positive pole. We also have a place for water vapor to get out, because this is one of the products and we need to get rid of it. And it's water vapor, by the way. That's why it says G. It's not liquid water. It's vapor. It's steam. Okay. And here we have the oxygen tank coming from air. This is the hydrogen tank coming from big tanks. And the electrolyte is going to be potassium hydroxide solution, which is KOH. This is our electrolyte. Why? Because we need a source of hydroxide ions in order for this reaction to go on. Our electrodes are inert electrodes. We are using carbon electrodes containing a catalyst. Why? Because this reaction requires a lot of heat, and we need to reduce the conditions that this reaction requires, and that's why we're using a catalyst. The catalyst we're using is platinum catalyst. So, just in order not to confuse yourself, this is the electrode, and it's impregnated, which means that it has some holes in it that have platinum catalyst. However, the electrode itself is made of carbon. So whenever you're asked about the electrode in the hydrogen oxygen fuel cell, you have to mention that it's made of porous material, like carbon, impregnated with platinum catalyst. The negative electrode, make sure that you mention that it's surrounded by hydrogen, while the positive electrode is surrounded by oxygen. If we get back to the cell, you will see that the positive is the one with the oxygen, while the negative is the one with the hydrogen. Alright. From there, the reactions are the same. So, a hydrogen gas reacts with two hydroxide ions coming from our electrolyte, which is KOH, K positive, OH negative. So this is coming from here. That forms two H2O molecules, which is the steam that we agreed on that gets out later on, and two electrons are lost in this process. That's why we have two hydroxide ions in here, because the hydroxide is the one that's going to be donating the electrons. At the positive electrode, one oxygen atom, that's why we have half O2, will be reacting with H2O. Now, if you think about it, this is water, HOH, and this is one oxygen. So this one oxygen is gonna go here, and then we're gonna have OH, OH. So this is 2 OH negative, right? Which is this guy right here. Okay, so this is basically how this reaction happens. This oxygen, one oxygen atom takes this proton with the hydrogen plus, forming OH, and we already have OH from water, so two OH ions are formed. Now, if we add up these two reactions together, you will see that water, one water molecule is going to be taken out. So this 2 will take out, or one of the H2, of the two H2O molecules here was used as a reactant later on. So ultimately, we only have one H2O molecule formed, and the reactants are H2, H2, and half O2, half O2, and that forms H2O. Okay? Now, the electrolyte must contain hydroxide ions as we discussed, so it could be sodium hydroxide, could be potassium hydroxide, whichever you prefer. And let me just correct something. This is not liquid, this is actually aqueous. Sorry, this is actually gas, sorry, because we agreed that it's vapor. Now there are some benefits or advantages and some disadvantages. As you can see in this reaction, there was no mention of carbon dioxide at all. So no pollution, zero emissions, no carbon dioxide. We are only forming water in vapor form, which is steam. It releases a high amount of energy, which means that this is an exothermic reaction, which we will talk about in the upcoming lessons. It works continuously. There's no need to recharge it as long as you're providing it with hydrogen and oxygen. Lower flammability than petrol, and technically it's emission free, like we didn't really form any gases other than the steam, and it's non-toxic, so it's very environmentally friendly. When it comes to disadvantages, it's a large fuel tank, and there are few filling car stations currently because of the large tanks required, and it's really expensive because the process at which you need to form hydrogen in the first place is an expensive process, and it requires special car engines, of course, to suit this kind of fuel. Okay, so basically these were the advantages and the disadvantages, and an overview of the hydrogen oxygen fuel cell. And with that, chapter 6 electrolysis is over. I really hope you guys enjoyed it and you learned a lot from it. Don't forget to subscribe to the channel, leave your comments in the comment section below. A thumbs up to the video will be greatly appreciated, and I will see you guys in the next video. Take care.